On October 4, 2022, Meta's Facebook, Instagram and WhatsApp went offline for nearly 6 hours. 800 million people couldn't log in. The estimated cost was around $100 million in lost revenue. The cause was a configuration change that sent incorrect data about network capacity. That's a famous outage, and the root cause was networking. But here's a less famous fact. Some of the hardest parts of the post-incident investigation involved reconciling timestamps from servers in different time zones that had logged the same sequence of events with different times attached to them. Engineers couldn't agree on what happened first. Date and time data does that. It turns a clear sequence of events into a puzzle. And that's one of the milder things it does. Most people assume dates are simple. A date is a date, a time is a time. You store them, you retrieve them. What could go wrong? Almost everything. Dates are the only data type where the value you store is not necessarily the value you get back. Here's what that means. Imagine you live in London and you book a flight at 11 p.m. on Saturday night. The airline server is in New York. Your computer sends the booking time as 11 p.m. The server in New York receives it and thinks, 11 p.m., that must be Eastern time. It stores 11 p.m. Eastern, which is 4 a.m. Sunday morning in London. Your booking confirmation says Sunday. Your calendar says Saturday. You show up on Saturday. The flight left Sunday. This is not a hypothetical. Time zone confusion in booking systems has caused exactly this kind of failure. And it happens because a date time value, on its own, means nothing without a time zone attached to it. A time without a time zone is like a distance without saying where you started measuring from. It looks like information. It isn't complete information. But time zone confusion is only the first layer. Let's go deeper. Twice a year, in most countries, the clocks change. 1 hour forward in spring, 1 hour back in autumn. Most people experience this as a minor inconvenience. Databases experience it as an ambiguity that can break an entire system. Here's why. When the clocks go back in autumn, time literally repeats itself. At 2 a.m., the clocks roll back to 1 a.m. Every minute between 1 a.m. and 2 a.m. happens twice. If your system logs an event at 1:30 a.m., which 1:30 a.m. was it? The first one or the second one? If your system isn't handling this correctly, and many aren't, it has no way of knowing. Two events that happened an hour apart can appear to have happened simultaneously. An event that happened at 1:30 a.m. the first time appears to have happened at the same time as an event that happened at 1:30 a.m. the second time. Your logs are correct. Your sequence is wrong. In 2012, a major airline reservation system suffered exactly this problem during a daylight-saving transition. Bookings made in the repeated hour were processed in the wrong order. Seat assignments were duplicated. Passengers arrived at gates to find two people with the same seat number. The fix took 3 days and required manually reconciling thousands of records. And here's the part that makes this so persistent as a bug. It only manifests twice a year, at 2 a.m., for 1 hour. Most systems are never tested at that moment. The bug sits in production, invisible, until the clocks change. That's the unique cruelty of date and time bugs. They hide inside calendar edges. End of month, end of year, leap years, time zone transitions, daylight saving. Normal days, the system works perfectly. Edge days, it quietly falls apart. Let's talk about the leap year. A leap year occurs every 4 years, except when the year is divisible by 100. Then it isn't a leap year. Except when the year is divisible by 400, then it is again. 2000 was a leap year. 1900 was not. 2100 will not be. Most developers know the 4-year rule. Far fewer know the exceptions. And in 1900, many systems have a bug that will not reveal itself until February 28, 2100. It's already written. It's already deployed. Nobody alive today will fix it. But you don't have to wait for 2100 to see leap year bugs cause real damage. In 2012, Microsoft Azure experienced a major outage on February 29th. The cause was a certificate generation system that calculated expiry dates by adding 1 year to the current date. On February 29, 2012, it tried to create a certificate expiring on February 29, 2013. February 29, 2013 does not exist. The system crashed. Multiple Azure services went offline for up to 12 hours. The date was the bug. The certificate system had worked perfectly for years. It had never been asked to run on February 29th before. 1 day in 4 years. 12 hours of outage. Thousands of businesses affected. Now let's talk about something more subtle. 2 engineers at the same company store a timestamp. The first stores it in UTC, the Universal Reference Point. The second stores it in local time, because the application runs in one time zone, and it seemed simpler. 6 months later, the company expands to a second country. Suddenly, half the timestamps are UTC, and half are local time. They look identical. There's no flag, no label, no column telling you which is which. You can't tell from looking at a value whether it's UTC or local. So when you sort them, some are correct, some are an hour off. The report is wrong in a way that looks almost right. This happens constantly in systems that grew faster than their data model. Date and time data encodes more assumptions than any other type. Every date time value carries hidden context. What time zone is it in? Does it account for daylight saving? Is it the moment something happened, or the moment it was recorded? Is it a point in time or a duration? Store a number and you know what you have. Store a date and you have a number, plus a calendar system, plus a time zone, plus a set of rules about exceptions, plus an assumption about whether the clock was adjusted. All of that is invisible inside a single column. So how do you protect yourself? The first rule is one that engineers argue about and then almost always agree on eventually. Store everything in UTC, not local time, not the server's time zone. UTC. UTC doesn't change. UTC has no daylight saving. UTC is the same in London and Tokyo and Sao Paulo. Convert to local time when you display it. Store it universal. This single rule eliminates an enormous class of time zone bugs. The second rule: always store the time zone alongside the time. If you cannot store in UTC for a reason beyond your control, at minimum tag every date time value with the time zone it represents. A time without a time zone is an incomplete value. Treat it that way in your schema. The third rule: test your system at the edges. December 31st into January 1st, February 28th into March 1st, February 29th on a leap year, 2 a.m. on the day clocks change, midnight in a system that crosses time zone boundaries. These are the moments your date logic will fail if it's going to fail. They never occur during normal development. You have to manufacture them deliberately. The fourth rule: use your language or database's native datetime type, not a string, not an integer. A date stored as 2024-03-15 in a string column can't be compared, can't be calculated against, can't enforce valid values. March 45th is a valid string. It is not a valid date. Let the type system do the validation work it was built to do. Dates feel simple because humans have been reading calendars for thousands of years. They feel natural and obvious. But to a computer, a date is one of the most complex values it can store. A number that refers to a human convention inside a time zone system invented for political reasons, governed by rules about leap years that have exceptions to the exceptions, affected by a twice-yearly clock change that makes time literally repeat. Every system that stores dates will eventually meet an edge case it wasn't designed for. The question isn't whether it will happen, it's whether you are prepared.